thing with the D flip-flop with using the NOR gate, which was in your homework, okay? And kind of get the point of it is, the point of these homework is not to torture you with, a bunch of logic stuff, but to get you thinking about how these little components actually work inside your computers. And then so if I can maximize my screen, that'd be nice. Okay. All right, OneNote just decides to crash because probably a memory allocation went wrong, right, in my operating system, and therefore it crashed. One was supposed to be a 0 was supposed to be a 1 at some point, and then and then some checksum probably failed. Okay, so I think I went through this last time. I don't even know when. This is like 3 lectures ago, something like that, when we talked about memories, right? This is called a D flip-flop. D stands for data, right? And this one is made of NAND gates, and then the one in your homework is made of NOR gates and AND gates. Typically, they make it out of these because it's just simpler to make, lots of NAND gates versus dealing with NOR gates and AND gates and placing them in the right place. And I already spelled out the truth table, but the idea is that this is known as a flip-flop, right? Where whatever Q is, right, on the other side, the other output is always the opposite. It just kind of flips back and forth. And the weird thing about this is that the output of this NAND gate goes to the input of this NAND gate, right? So it's kind of this, like, chicken and an egg. No, well, chicken and egg actually makes sense. A catch-22, right? Because those of you who took biology, right, knows that genetic changes happens at at the fertilization, right? It does. So therefore, right, the eggs actually came first, right? Genetically, eggs are first. Sorry, let's not talk about that. People are bored. Okay, so, right, how do you deal with this, right? Because you don't know what Q and Q bar is, and those are inputs to your second pairs of NAND gates, right? So, for example, here, right, I think I didn't give you guys this example where, the output is actually kind of confusing, right? Let's say, D started off as 0, so I'm even going to mark it up here, right? So 0 here, that means the input to this inverter gate is 0, and I don't need the keyboard, okay? That means here's 1, right? And the clock, let's say, started off at 0, right? So 0, 0, okay? And over here is the truth table for a NAND gate, right? Because we're just dealing with NAND gates, right? The only times a NAND gate gives 0 as the output, right, is when both inputs are 1s, right? So just by knowing that at least one of the input is 0, right, I know that the output here is always going to be 1 without even checking the second input, right? Happy? Okay. All right. So since one of these input is 1, right, but I don't know if the other input is 0 or 1, so therefore I actually have no idea what Q and Q bar is. Okay, so I cannot determine that at this point. Okay, and then you'll find out that, well, what if I flip this, the clock goes from 0 to 1, okay? So it's 0, and then and you have a positive edge going up, okay? We're going to see this in FPGA when we program these things, right? When this goes up, right, that means D bar and clock, right, these two inputs are now 1s, right? So D bar is down here, and the clock, instead of being 0, is switched to 1, okay? Now, right, 1, 1 on the NAND gate gives you 0 as the output, right? So once I know that, right, so this is 0 as the input to this NAND gate. If any of the inputs on the NAND gate is 0, that means the output is 1 right away, right? I don't even need to know what the other input is, right? Okay, so therefore, right, just by, let's just mark this X and mark this Y, okay, just for these rows, columns, okay? Since Y is equal to 0, I know right away Q bar is 1, okay? If I know Q bar is 1, you can go through the logic and then put 1 as the input here, right? 1, 1 gives you output through a NAND gate, gives you an output of 0, right? Or you can just think, well, if I know Q bar is 1, Q has to be 0, right? It's always the opposite of each other, right? You can go through, it'll work either way, okay? So let's see what happens when I flip. So this was the clock being high, right? And then while D is being low, right? Let's see what happens when I flip D from 0 to 1, right? Let's say I switch the input, right, in here from 0 over to 1, okay? When that happens, right, D bar becomes 0, okay? The clock is still high. We're still leaving the clock alone for this point, right? But instead of X being 1, now X is 0 because, right, so if we have D equal to 1 here, right, this changed to 1, so 1, 1 on a NAND gate gives you 0 as the output, right? And then, oops, that stays the same, right? And then, since this is 1, the opposite of 1 is 0. 0, 1 through a NAND gate gives you 1 as the output, right? And now, you know, while I know that this one input through a NAND gate is 0, so therefore I know Q is 1 for sure, and then Q bar is always the opposite of it, right? So you notice that when the clock is high and you switch your input from 0 to 1, right, your clock, sorry, your D basically gets copied over to your Q, right? And Q is usually the output for these things, the non-inverting output at least, okay? Right? And then if we go back one more row, right, we notice that, well, when D was 0, Q was 0, right? So the two actually follows each other if the clock is high, right? And then if I flip this back down, right, the next row here, just to kind of be a little bit long-winded, because I think I was in a rush last time, right? If I flip my 1 back to 0, right, basically what happened is that, if I, okay, let's go from here, right? So we started at 0, we switch it to 1, now we switch it back to 0, right? Now this input here is 0, okay? The clock stays the same because we're leaving the clock alone at this point, right? This input here becomes 0, this becomes 1, right? All these kind of get flipped upside down, and maybe hopefully now you see why they call these things flip-flops, right? They just kind of flip, right, every time you go through it, okay? So therefore, right, when your input goes from 0 to 1, right, your output goes from 0 to 1 also, right? The two just follow each other, okay? Now that comes the interesting part, right? Right? Remember before I was not able to figure out what the heck is going on when the clock is low. But now I can, because now I know the output on the other side, initially at least, right? Okay? So I'm going to do two things at once. So I'm going to flip, right, the clock from high to low, right? And I'm going to flip 0 to 1, right? Does that change anything, right? Does that do the same thing as what happened this time, right, when I went from 0 to 1? Okay? Meaning, is this going to happen, right here? Okay? And hopefully you see it's not, okay? Okay, so what happened is that, right, if the clock goes from high to low, right, this is my third step, right, and I'm flipping this. This goes to 1, this goes to 1, right, the opposite of 1 is 0. But this time, right, the clock is low also, okay? Therefore, right, all of these always, oops, I erased the wrong thing. I didn't want to erase the Y, I want to erase the output Y, right? This will be a 1 as the output. This will also be a 1 as the output. Okay? All right. And what was the initial state here before we change anything? Q was 0, right? Q bar was 1, right? Okay? So now you see that Q bar being 1 here actually does matter because you have a 1 connected back up here again, right? Okay? So 1, 1 gives you 0 as the output, right? 1, 0, oops, sorry, 0, 0, right, because this is also 0. Connect down here. Oops, sorry. This 1 gets propagated forward. This is why it's confusing, right? Because I keep not erasing all that stuff from previous steps. Okay? And I write it multiple times also. I should just write it on the wire. Okay? Right? This whole wire is high, right? 5 volts or whatever it is. Okay? So therefore, right, 1, 0, I mean, it doesn't really matter. As long as one of the input is 0, you know the output is going to be 1, right? Or the other the other way to figure it out is that, well, if you know this is 0, then the other one's 1, right? So the interesting thing is that, right? Okay, when we did this flip from on green, right? We changed the D from 0 to 1, right? The clock from 1 to 0. The output doesn't change, right? Okay, and this is what the homework is trying to get you to realize when you do this with NOR gates and AND gates. Okay, right? As long as the clock is low, right, the outputs can never change. Okay, right? When clock is 0, Q equals to the previous Q. And I think the little algorithm that the book try to denote is that the next Q, which is Qn plus 1 equals to Q. That these two statements are saying the same thing, right? N is like the nth clock, like if like the 2000th clock cycle, right? Okay, but what's Q in the 2001 clock cycle, right? It's the same thing in that case. Okay, does that help clarify how these D flip-flop works? Because we're going to use them over and over and over again. Okay, and when you do this with the NOR NAND gate version, it'll be the D and the Qs will be exactly the same, but then the XYs are different from each other. That's all. Okay, the tables are slightly different. Okay, so just be careful. Okay. All right, any questions before we start talking about counters, which is our next section? I think I'm recording already. We good? Everybody understand D flip-flops? Because it's like there's like every day you're walking around with like 5 trillions of them in your pocket, in your backpack. Okay, because that's basically all RAMs are made of this. Okay. Okay. Now let's talk about how we can use these D flip-flops and the clock to do some. I'm not sure if we can call this math. Well, we're going to count. Okay, and this is why these things are called counter circuits. Okay, so a lot of times, right, on a computer, it doesn't actually care how long 1 second is, or 1 day is, or 1 year is, right? Those are human things, right? So what we human program computers to do is actually to count times in terms of seconds, okay? And this is actually called either pronounced epoch time or epoch time. I actually don't know which one is correct. To me, it looks like epoch, but then people pronounce it epoch, okay? And the epoch time is basically not basically, it is defined to be the number of seconds since midnight, January 1st, 1970. Okay, why 1970? You know, that's when like a lot of computers got more popularized, right? You know, there were computers before 1970, of course, but you know, they didn't have the same epoch time to keep track of things. Okay, so in fact, you can just go to this epochconverter.com, right? Type in the day and the time right now, and then it'll convert that time into epoch time for you. These are also like known as computer timestamps or operating system timestamp, Linux timestamps, right? This is the number of seconds since this midnight, January 1st, 1970. Okay, and that's how your computer keeps track of time. It's just counting number of seconds. Okay. Okay. In order to do this, right, if you have a 32 bits of memory, okay, 32 bits of memory allows you to count up from 0 to 2 to the 32, because we don't have to care about negative time, right? Right? There's no time before 1970, I guess. Okay. I wonder what happens when you try to enter in a time that's 1969 or something like that in the computer. It's just going to explode or crash or something like that. Anyway, so 2 to the 32 allows you to count up to 2.3 trillion seconds, okay? Or if you convert that to years, it's 136 years. So basically, we're going to run out, I mean, if you have a 32-bit operating system, you're going to run out of time in December 31st, 2105, okay? I guess that's the, what is that called when people interpret books and say that it's the end of the time? I'm sorry? Y2K. Y2K is a different problem, actually. That's just the SIG thing. No, like when people say like the apocalypse is here and then it's the end of the world, what is that called? Or like it's like a Mayan calendar ending or something like that. I'm sorry?
Prophecy.
Prophecy. I don't remember what it is. It's like some sort of it's the end of time, right? Or whatever that was called, right? Yeah, the world just end and then you drink your Kool-Aid and you go with the go with whichever belief you want. I mean, people. Okay, well, all right. Anyway, that's just an interesting time. Okay, you guys might live long enough to see that, right? And when 32 bits, in that time, you may have people saying, "Oh, well, the 32 bits, you know, clock counters that keeps track of time since 1970, right, has ran out. We're gonna all die or something like that. I don't know. Okay, we'll see. We'll see what happens. Okay, but you can see how these things are really arbitrarily set, right? You know, if you increase it to 33 bits, you would, you know, this would be a different number of seconds, right? All right, in fact, right, ooh, this is a crazy thing. Different operating system keeps track of time differently also. So for example, if you're using a Windows computer, it can keep track of time down to 100 nanosecond or a tenth of a microsecond, right? And actually it does this by not only keeping track of a number of seconds, right, with this 32 bits, but, oh, I didn't write that down, but it also has, you know, so there's a little memory bank, you know, let's say a 32-bit memory bank that keeps track of number of seconds since 1970, but there's also a second memory bank, right, that keeps, you know, maybe is 32-bit also, right? That basically number of nanoseconds, right, sends that 1 second, right? So it just keeps track of all this time. Okay. Okay. So a Windows computer can do things down to a tenth of a microsecond, and one of the reason why a lot of scientific computing uh, utilizes Linux computers is because it can keep track of time down to 1 nanosecond. So it's 100 times more accurate compared to a Windows operating system. Those of you who are using Macs, sorry, you can't really keep track of time that well. It's around a millisecond. That's how well that operating system keeps track of time. One of the reasons is that, right, in order to keep track of time, you know, sub-seconds amount of time, right, you need to dedicate memory to keep track of that all the time. Okay, so the way that a Mac operating system saves time is by not counting this very accurately, right? Maybe it only uses 8 bits to count this, right? Or something like that, okay? But you may think that, well, why do I care about, you know, things down to 100 nanoseconds or even 1 nanoseconds, right? So a lot of experiments actually, you know, count things, right? So a simple experiment, so some of you guys might seen this already, right? If you want to count the number of muons passing through a detector, right? Maybe a muon passes through a detector, and this detector is designed so that it makes a little bit of light whenever a muon passes through it. You detect the light, and the light gets counted, right? You see a little check mark here. Oh, light went through, right? And then it passed through a second detector, light went through, right? So you can count, right? 1 muon, 2 muon, 3 muons, 4 muons, you know, how many times this light actually turned on, right? It's like me doing, well, I can't do it here, right? Because these lights are kind of dumb. Uh, I can't just flip the switch on and off here. Okay, so these type of detectors, right? Especially if you're dealing with just muons, right? You will maybe see something about 100 muons per second, maybe even a few thousand. You have a big enough detector, so you just need to count, right? Once every 10 millisecond, 1 millisecond, right? That's pretty easy to count. Even the Macintosh can count that, right? But, right, if you're inside a particle accelerator, where you have to count things at 25 megahertz, right, 25 million times per second, now you need something that can count, right, to keep track of time down to, like, you know, nanoseconds, essentially. Okay? So different number of bits, right, of counters, right? So if you have a, let's say a 8-bit counter to track time, track the sub-second time, right? You can only split that time, right? That you can split 1 second to 2 to the 8, right? And 2 to the 8, I think, is 256, right? And 256 is about 0.4-ish milliseconds, right? And that's basically how well a Macintosh keeps track of time. But if you were using a Linux operating system where it keeps track of time down to the nanoseconds, right? It actually does this with 32 bits of memory, right? 1 over 32 bit is 4.3 trillion, right? Trillion is 10 to the 9, right? So it can actually keep track of time down to 0.025 nanoseconds, okay? And you're just investing resources to keep track of this time, right? Because you may not want to spend too much. If you're, us as human beings, right, we can only see things on the order of, tens of milliseconds, right? I can't tell the difference between, something that's 10 milliseconds than 11 milliseconds, right? So if you're just using like, a phone, especially like a phone or something like that, you don't need something that's fast, right? But if you're running a physics experiment where you're colliding protons and protons together every 40 nanoseconds, you do want to keep track of time very well, down to the nanoseconds. Make sense? So, how do we do that? Okay? You do that with what we just learned, D flip-flops. Okay? And I think we kind of already reviewed what a D flip-flop does, right? A D flip-flop, the operational diagram, right? We have some data coming in, right? And you can have some clock coming in, right? And then you can have Q. Sometimes you will have Q bar also, but a lot of times you may not actually care what Q bar is doing. I think in this case we do, okay? And this is known as a D flip-flop, okay? Okay. I think there's chip. Yeah, one of the chip is a D flip-flop. I forgot which number it is. But in your FPGA, you can actually just connect these things together pretty easily, right? Because a D flip-flop is just 4 NAND gates, right? Okay, and inverter gate. Okay, but right, you want to utilize this functionality of a D flip-flop to count something. So how do we do that? Okay, so this circuit down here is a 3-bit counter. So if it's a 3-bit counter, how high can it count in decimal? 3 bits. I'm sorry? 4. Well, how high can the number be with 3 bits, right? So the third bits has a value of 4, right? This will have a value of 4, this has a value of 2, this has a value of 1. You can count up to 7, right? Well, you can count from 0 to 7, okay? Okay. All right. So this is kind of a complicated diagram, and I don't expect you guys to design this out of, thin air, right? I do expect you guys to take this and make it 6 bits and 7 bits and stuff like that, right? Hopefully that's okay, right? But let's see how this works, okay? So one of the neat thing is that, right? So the power here, right, is supplying to this S bar and R bar here. The reason you do that is that, so remember that when S bar is 1, when S is 1, right, that means you cannot change the output here. So you want to get this so it's always 0. By putting 5 volts to it, what you're doing is you're basically making S bar equals to 1, so S is actually equal to 0. Hopefully that makes sense. Okay, that's the way that these things are designed. Okay, but okay, so that's just to kind of set things up, and you have to supply 5-volt VCC to it and ground and stuff like that. Okay, the actual circuit that makes it a counter is the fact that what you're doing is you're going to connect the input here to the output bar, Q bar. You see this weird loop, right? And then your real input is actually just a clock that's coming in, okay? And the clock is pulsing up, down, up, down, up, down, okay? Okay. And similarly, right, the next D flip-flop is also connected up like this but instead of taking the clock as an input, it takes the Q bar output of the previous D flip-flop as an input. And this just goes on and on and on and on and on, okay? All right, everyone happy with this diagram? No? Bored? Okay, yeah, so let's see how this works, right? So, okay, so here we have a little timing diagram of the clock going up and down, up and down, up and down, just a square wave, right? Okay, so let's say what happens in cycle number 0. So I make this little diagram so we can actually figure out what's happening at cycle number 0, okay? Now cycle number 0, right? We're going to call this is going to be the D flip-flop 0, right? So this input here is going to be called clock 0, right? A lot of symbols, okay? This is D flip-flop number 1, so this will be clock number 1. This will be clock number 2, right? And then so same thing with the D's, right? 1, 0, and then the Q's, we don't, and then the Q bars and the Q's, right? I'm going to label everything, 0, 1, 2, okay? All right. So, right, let's say, right, we're timing this, so we're lining this up like this, right? At the first cycle here, right? Well, C0 is going to be whatever the clock is. The clock is high at this point, so we'll just put in a 1 there. Okay? Okay? If this is 1, it is going to send whatever, right? So think of the clock as kind of like a little trigger, right? It's going to trigger whatever D is going to get sent to Q, right? And Q is going to be opposite of Q bar, right? Right? So that's going to be a little bit funky, right? Because we actually don't know what Q is in the first place, okay? So we're going to set Q to be some initial state, okay? And if you want to start counting, right, you want to start counting from maybe 0. You can start counting from 20 if you want, right? But you can make counting from 0 hopefully make sense, right? Let's just make, right, these outputs here, right, which is connected to Q0, Q1, Q2, right? Let's start counting from 0, okay? Okay, so that's information we have. And that means Q bar are always opposite of it. Okay, I'm just filling this table out with the stuff I know. Okay? Okay, all right. That means, right, if Q bar is 1, that means D is equal to 1, right? Because this is hardwired together through a wire. Well, through the wire. Sorry. Okay, so that means, right, what 1 is going to be passed from D to Q when the clock is high. Okay? Okay? So D is also going to be 1. Okay? So all the D's are going to be the same as the Q bars, right? Because they are connected together through this wire. Okay? Okay? All right? And then C1 here is whatever Q bar is, and so C1, right, is the same as Q0, right? All right, everyone follow me? It's this little maze here, right? We're just trying to decipher one wire at a time, okay? Okay. So C2 is going to be the same thing as, oops. C2 is supposed to be Q1, right? But Q1 is 1, okay? All right. I might have started this at the wrong pace, but we'll see, okay? All right. So this is kind of our starting point, right? The next time the clock pulses high, the next clock cycle comes around, right? It's going to go high again. Okay, C0 is still going to be 1. You're going to notice that this is always going to be 1, right? Because the clock is always, we're waiting for a clock to pulse high for something to happen all the time, okay? Okay, right? So this clock, right, what happened is that D0 gets transferred over to Q0, right? Because that's what happens when the clock pulse high, is whatever information is here gets sent over to the output. Remember, if we go up here, ooh, okay, right? when the clock is high, right, whatever is the input gets sent to the output. Okay? Happy? No? Sad? Confused? A little bit? I'm confused too, maybe. Okay. So that means whatever is here gets sent here, right? So it's forcing Q0 to be 1. Okay? If Q0 is 1, Q0 bar has to be opposite of it. That's how a D flip-flop works, right? So switch that to 0. Okay? All right? So that means, right, if Q0 is 1, if Q0 is 1, Q0 bar is 0, okay? And remember, Q0 bar is still hardwired to D, right? It's still wired to the input, right? That means it's going to send this information back here and make the input there 0 for next turn. Okay, so the information already got passed along, and then it changes what the input is, and now the new input is ready to be used. Okay. Okay. So what happens that, well, since it would also change Q0, right? And Q0 is also connected to clock 1 directly, right? That's going to also change, right? So I'm going to draw the part where the changes happens, right? Right? D0 got this, D0 got this, right? Right, this stays the same, okay? And the rest stays the same because, right? D0, D1 depends on what Q1 is. We haven't changed Q1 yet, right? Because we haven't changed Q1 bar, and since we didn't change Q1 bar, we didn't change Q1 either. Sorry to be kind of long-winded. This is kind of the path you need to follow. So this is why these tables are so big, right? Let's go through this a few more cycles, okay? And we're gonna see why is this thing counting, okay? Okay, just trust me that the rest of these things stays the same for now, okay? Okay. So let's read out, right? The output here, right, is Q0, Q1, Q2, okay? The end result here is what you actually see on your LED or whatever it is, right? So the first time you get, right, it's going to be 0, 0, 0, right? Because I'm just reading out Q0, Q1, Q2, right? On the first clock cycle number 1, right, Q0 got turned into 1, the rest stays the same, okay? So the decimal value here is 0, the decimal value here is 1, okay? Okay, let's see what happens on clock cycle number 2. Guess what the next number is going to be? Okay, it's going to be 2, right? All right. Okay, as usual, right, I'm trying to line this up so that the clock pulse is high, right? So C1 is always going to be 1, okay? You can just keep going on this, okay? We may not go to 10 because that's going to take forever, okay? Right, remember when C1 clock pulse is high, right, it sends whatever the input is to the output, right? If the input is D, the output is Q, right? So it sends 0, it make Q0 equal to D0, right? So this actually turned it into 0. You guys see that? Okay. And of course, the Q bar, right, is going to be opposite of that, right? And this went back in time and changed this back to 1. Okay. Right? And since Q bar is directly connected to clock number 1 through this wire here, right, this is going to change to 1. And now the clock of the second flip-flops goes from 0 to 1. Okay? When that happens, right, it's going to send whatever information is being held by D1, it's going to send it to Q1. Right? So that's going to have 1, it's going to send this 1 here, right? And then Q1 bar is going to be opposite of Q1, and therefore make those 0. Okay? Clock number 2 doesn't change, so we can just, oops, no, it does. Clock number 2, right, is connected to Q1 bar, and Q1 bar is 0, it actually goes down to 0. Okay? But the rest of the third flip-flop doesn't change. All right? Now let's read this out. Okay? All right, let's highlight this row here, right? Oops, if I can draw a straight line. Right? So after the second clock cycle, right, I have 0, 1, 0, right? And that's equivalent to 2, okay? And then the next one is going to be 3, the next one is going to be 4, right? And then we can count up to 7, basically, right? I don't think I'm going to go through all of them, though, okay? Because you guys are going to fall asleep already, okay? Do you want to do one more cycle, or we get on this pattern? One more? One more? Let's do one more cycle, okay? I mean, you're going to see this in the lab, and you're going to see this in these timing diagrams also, okay? All right, let's do one more cycle, okay? Right, so the clock, the pulse is high, so whenever that happens, right, on D flip-flop 0, it sends the input to the output, so it changes to 1, okay? So when it changed that to 1, Q0 bar, right, gets flipped, right, because it has to be opposite of Q, right? And that's also connected to these two guys, right, D0 and C1, right? So that it forces those to be 0, okay? But the transition from 1 to 0, it does not trigger the D flip-flop to send this information, right? Only from 0 to 1, right, we have the D flip-flop will send information forward, not the other way, right? Okay? Only on the up transitions, okay? Okay? So therefore, right, D0 stays the same, Q0 stays the same, Q1 bar stays the same, C2 stays the same, the rest stays the same. Okay? Now if we copy this down here, right, we have 1, 1, 0, which is equal to 3, right? And then the next one, what's going to happen, let's just do one more just to see the third flip-flop in play, right? Okay? How this is also known as a ripple counter. Okay? And you can see why it's called ripple counter. It's like a little ripple going along the D flip-flops. Okay? All right, sorry, just do one more. Okay? So the next clock cycle, right? The clock on the first flip-flop goes from 0 to 1, so it sends the information forward, right? It flips this, okay? Okay, since this got flipped from 0 to 1, it forwards the information from, oops, not there, from D1 to Q1, right? So that's 0, right? That flips Q1 bar upside down, and then C2 got flipped upside down also, which also forwards this information to the next guy, right? So the D2, which is the input for the second flip-flop, flip-flop number 2, goes to the output of flip-flop number 2. That flips all the other ones. Okay? And now, if we copy the information over, 0, 0, 1, right? Okay? And that's equal to 4, right? And I see Uriel's asleep, but that's okay, because I would be also if we keep doing this, right? And then you can see that this is going to just keep counting up. Okay? Right? So here's your little counter. Okay? Right? Really boring to go through it. Okay? And you guys get to go through this a little bit more. Okay? I'm not sure how many bits I have you guys go through this, but it's less sleepy when you have to write it. Okay? Does this make sense with everyone? How this work on a physical chip? Okay? All right. So you can make this on Verilog easily because in this week's lab you're going to learn how to make a clock and how to make a D flip-flop on Verilog. Okay? Okay. So, so this counter lab is going to be next week's lab. You guys are in lab 10 this week, right? 11. Okay. This is just to make your life a little bit easier, right? So once you write the Verilog descriptors, I'm going to call it code. Okay, it's not really code, but the code, right? For your clock and the D flip-flop, you may want to reuse it again, right? Okay. The way you find it is by going into your FPGA folder, go to this, maybe your lab 10, right? And inside that folder, there's a folder called .source. SRCS stands for source. And then inside that source, there's a source _1. And under there's also a thing called new. And there you can actually find your top file. When you open your top file, you can actually copy and paste your code from your previous project to your current one. Make sense? Okay. Of course, you can actually open the previous project, right, and then have the whole project open, and then just copy and paste that into a text file, and then paste it into your new project. But you know, this is easier, I think. Okay. Okay. Just so that you know how to copy and paste code forward, because that's going to be very useful. Because you're going to keep this D flip flop, you're going to use it over and over and over and over again. Because once you make it, there's no reason to write it again, right? Okay. Okay. On top of that, next week we're going to have you guys learn how to use this thing called the resistor transistor logic analysis, also RTL analysis. Okay, where it's really cool, right? You have, if you put this code in here where there's a clock, there's some flip-flops. Okay, you're going to be building these code today and tomorrow. Okay, it'll actually, once you compile it with the, once you synthesize it, okay, you can actually have it make the design for you. So this is like a schematic, right? You would draw on a piece of paper, right? So this is like a slow clock that's going into your D flip-flop, and your D flip-flop, you know, has the D input connected to the Q bar output. So this is actually the ripple counter we just talked about. Okay, right? And these are the LED outputs here, right? You know, 0, 1, 0, 0, 1, 0, 1, 0, right? Etc. like that. Okay. Okay. The way you get to this is once you synthesize your code, you can go to this place called RTL analysis, okay, and have it generate an elaborated design. Okay. And once you elaborate the design, it'll take like a minute. Okay. It'll make this diagram for you. Okay. And this is very useful for you to debug what's going on, because if you hooked up this wire over here, it'll show you. Right? It's a very nice debugging code because, right, it's basically trying to remake what you have in your schematic. One more point, it may not arrange things nicely like this for you. So this D flip-flop may be like over on this side, because it doesn't actually know, you know, what you're trying to design, right? It's just trying to connect these wires for you together. Okay? So initially it might look a little wonky, okay? Especially, okay, this is where organizing your code is important. If you put this line of D flip-flop 0, maybe at the end here, instead, it'll put things in weird places for you. It's going to try to follow the order that you coded it in, okay? So when you're writing your Verilog code, try to make the order that you might writing things as close to how you're building the circuit together in your schematic as possible. Okay, and then we'll try to put it in the right order for you. Okay? Happy? No? Sad? Everybody asleep? Alright. Ooh, it's been almost an hour. Okay. So let's cover one more thing that's a little bit more applicable, as opposed to just counting time. Okay? There's also these things called shift registers. Okay? Shift registers is very useful. Every time you plug in a USB, you're using a shift register. Every time your computer is moving data around, you're using a shift register. And one of the applications we're going to think about is how we send digital data in serial versus in parallel to each other. Okay, so now let's think about what USB is actually doing. The universal serial bus that everybody uses to charge their phone, send data, put in USB drives. I don't know. I used to play video games with other people with this, because back then it wasn't like internet games or something like that. I don't remember. Okay. I don't know if it was serial. Yeah, it was serial. Okay. Let's not talk about too long ago, back in the dinosaur age. But I'm sorry. Yeah, you need to have like a special cable. So USB is universal serial bus, right? The original version has 4 wires in it, right? Has a well, this is basically ground, negative, right? And this is 5 volts. Okay, This is data plus, data minus. Okay, so it basically just sends data via one little ups and down. Basically, it sends it out, right? So D plus, let's say D minus is always going to be 0, right? And you can set it like that. Okay, and then this is information you're sending. Okay, this is 1, this is 2. How do you send 1 1? Right, the next cycle you send 1 1. That means 3. Right, you're just sending information 1 bit at a time. Okay, but you're just doing this like 4 million times per second. That's why you can send 4 megabits per second. Right. Okay. But what's happening is that inside your computer, right? Maybe you have a little memory bank like this. Let's say this is a 4-bit memory bank. 4D flip-flops, right? Remember, one flip-flop stores 1-bit information, right? 4 of these guys, 1, 2, 3, 4, right? Each of these has a queue, right? Q2, Q1, Q0, right? Right? How do you get all of this information out in through a single series of numbers, right? How do you do that? Okay, right. So this is known as parallel in serial out algorithm, okay, or PISO. Okay, so the schematic of this looks like this, where you have, well, instead of Q's, they use D's for data. D4, DA, DB, DC, DD. Don't know why they use DD. Okay, right. And each of these blocks here is a D flip-flop that you can connect to. And you're going to say, wait, I thought D flip-flops are counters, right? This is a different thing, right? And the way you can use D flip-flop as a piezo is by just connecting the wires up differently, okay? It's exactly the same integrated circuit, but you just connect them together differently, and then you will have a different algorithm passing through it, okay? Okay. So as usual, the S bar and the R bar, we're just gonna have it on high, just so that the memory banks are accessible. Let's say. Okay. Right. So instead of just the clock only going into the first D flip flop, now the clock goes into every D flip flops. You guys see that? Okay. All right. And then the inputs, right, is connected to exactly what DA, DB, DC, DD is. Let's just call it D1, 2, 3, 4. And then the last, sorry, let's not talk about output yet. Okay, so that's the input. The output here is connected of D flip flop 1 is connected to the input of flip flop 2, and so on and so on, until you get to the last one. The last one is known as the serial output. Okay, this is where this pulse comes from. Okay, and these D's are coming from the memory banks in parallel to each other. Okay, okay. So you want to output 1 bit at a time, right? At the serial. So what you're doing is you want to send out the information stored in D4. You want to shift this over, right? So you want to send this information out by shifting it over, right? When you do that, you want to shift D3 over so that it's up next, right? So this is why it's called a shift register. Each bit gets shifted over 1 at a time, and then the serial out get the information 1 bit at a time per cycle. You know? Everybody set? And this is why the name is called shift register. You're shifting this registry over, this information over 1 bit at a time. Okay? All right. So let's try to go through this not in like 20 minutes like last time with the other one. Let's hopefully I can give me some space. Okay. So let's put some random data into our memory bank, right? So let's make D1 initially, 1, D2 initially 0, D3 initially 1, and D4 initially 1. So that's equivalent to, so that's 8 plus 4 plus 1, 13. Okay? We're sending the information 13 out. Okay. Okay. So if so, this is D flip-flop 1, 2. Sorry, I started counting from 1 instead of 0. Okay. So, right, Q1 is directly connected to D2. So whatever D2 is going to be Q1. So these are going to be our initial state, right? 1, 1, right? D4 is connected to Q3. And S around, I don't know what SL is at first, okay? Okay. Okay. So the clock pulses in, right? Right? And remember, whenever the clock pulses, right, it's sending D from to Q, right? So D, whatever information is in D1 gets passed to Q1. Okay. Did that thing just lock and unlock? Okay. Okay. So, right, so this gets passed along. Okay, same thing, because you're sending the same clock to D flip-flop number 2, D flip-flop 3, D flip-flop 4, right? So this send is always going to happen for every flip-flop, okay? So you can see now that, like, whatever information is here, right, got shifted down 1, okay? Right? And since, right, Q1 is going to be the same thing as D2, so because they're hardwire connected like this, right, this will just get copied down, right? Well, the serial out doesn't matter, okay? Right, so I don't actually know what's in D1, okay, anymore, okay? But I don't really care, okay? Because we're gonna send out these 4 bits and be done with this sending, right? Okay, next clock cycle comes, right? Whatever is held by D gets passed along, right? So D3 gets passed along, okay? D4 gets passed along to here, okay? Okay, and then, right now, right, we have these 3 spots that we actually don't care what's in there anymore, okay? Right, and since Q3 and D3 are connected together by wire, these are going to be the same, okay? And then the next clock cycle, you're going to have this 1 going down to, oops, going down to, sorry, did I do that? Offset. D gets sent forward, right? D gets sent, this one, yeah, here's the D. D gets sent forward, okay? All right, and then this is the next D, it gets forward, okay? And then this is just a copy, okay? And the last clock, so all of this, I don't know what that is, but I don't care anymore because I already got that data. The last clock cycle here, right, the 1 gets sent over, this whole thing is just a question mark, right? So what you're doing is you're sending, right, initially, remember we had, the information is 1, 0, 1, 1, right? What you're sending out is 1, 1, 0, 1, okay? So it's going to send out the most significant bit first, right, and the least significant bit last, okay? Okay, and you want it that way because the most significant bit carries a weight of 8, right? That's the most important value you want to send, right? In case the data stops, right? At least you got, oh, it's around 8, right? Right. Even though you're trying to send the number 13, right? Because if you send the least significant bit first, you just have the information, oh, it's 1, which is much more different than 13 than 8, right? Okay. Everybody asleep yet? Okay, so that's how your serial port works, right? By converting the stuff that is stored in your memory, your RAM, right, and your D flip-flops into 1 bit information that can be sent out at a time. By shifting, basically you should think about this is that the data gets shifted over once every clock cycle. Okay? Until it gets to the output, okay? Let's just talk quickly about, how fast these things are, right? So when I was a kid, right, we had USB 1.0, which can do 12 megabits per second. Okay, so it's sending out 12 million bits per second. So this thing is going up and down 12 million times per second. Okay, okay. When we got to USB 2.0, okay, which is known as the high-speed inter-chip, standard, okay, somehow, right, is able to basically, multiply the speed by what, like 40 times, right? So that's about half a megabits per second. And I think I have some notes on how they actually did this. Let me open this up. Just kind of conceptually, okay? I mean, I'm not going to know the engineering details about this, but let's see. Grab that real quick, right? Oh, and so this is just done by increasing the clock speed. Wow, okay. Okay, so back, when USB first came out, right? These clock cycles, right? They were dealing with motherboards that would probably can only go at about 25 megahertz, and they want to be like friendly to all the devices. So, each of these clock cycle, right, is 1 over 12 million, whatever that number is, right? Okay, and by the time, right, USB 2.0 rolls around, right, basically this is not to scale, of course, right? They basically make these clock cycle much finer, right? So it's actually 480 times, million times per second, okay? Okay, but now, right, you guys are not using USB 2.0 anyway, right? There's a thing called USB 3.0, right? Before we get to USB-C, okay? The way you deal with USB 3.0, which this is shifted over. The reason I can send 20 gigabits per second is because not only does it have the same USB 2.0 interface, it also has 2 more channels, right? So there's an RX plus RX. So R means RX means receive, T means transmit, okay? So this is actually like 3 channels sending things simultaneously, okay? Okay. And when you do that, you not only triple the speed, because you can actually send information that are related to each other, you can actually have about, I think this is about 50 times faster, okay? And then now we have USB-C, which is, the one that everybody uses most of the time, right? And that has basically 2 of the original interface. And the reason for that is because USB-C is actually symmetric, right? So the top and the bottom are actually symmetric with each other, so you don't have to worry about which orientation things are, right? And then it also has the same TXRX as USB 3.0, but an additional um, a double, basically a second set of data bus that USB 3.0 doesn't have. That's why it only does two times faster. Okay, but the nice thing is that people like it because you don't have to worry about which way you're plugging in your USB anymore. Okay. Let's see. Should we talk about this last thing? Do you want to go the other way, where let's say, well, we're able to send data out from our hard drive or our memory, right, out through USB, but now the USB information is coming in serially. How do you convert that back into parallel, right? So there's also a conversion where you go serial in, parallel out, which is called SIPL. Very creative, right? Um, let's not go through the truth diagram, but just kind of see this schematically, how this is hooked up compared to piezo. Okay. Um, Similarly, instead of a so let's go back up here. Unfortunately, it's kind of far away, right? Right. The piezo circuit, right, has these digital parallel inputs, right? Okay. Now, right, since we're going to go SIPO, serial in, parallel out, right? The input is just a single serial input, right? And your output are these parallel, right, bits, right, that you're going to write to your RAM or whatever you want to connect that to. Okay. Right. And it's a very similar design except, right, because the shift register works the same way even if you keep going, right? So let's say you had your original shift register out here, right? You can keep shifting this data on and on, right? So if you have a serial input here, right, where you have a single channel ones and zeros coming in, right? This ones and zero, right, can be shifted over one at a time per cycle, and therefore start writing this information onto your RAM or your D flip-flop, right? The catch is, right, if you want to write 4 bits, it'll take 4 cycle for you to write that, right? Okay, so you cannot read it out every cycle anymore, okay? But and if you have 64-bit, computer memory in your computer, like most of our operating system, you have to write 64 cycles for you to read out the memory, okay? Um, and this is sort of a little cool thing, right? We saw that the information basically kind of ripples down, or just kind of goes down one step at a time. Okay, and we're gonna see how this actually works. Let's save this for next time because I'm already over by 5 minutes. On these things called simulation diagram, or actually the timing diagrams, um, for using your FPGA. So we're gonna see this. Unfortunately, this is upside down because they put 0 here instead of the other way, right? So you can see this data actually progressing through, and you can actually simulate this in your FPGA. Okay, so I think I should wrap up today.